You've been spending the last few weeks learning about motion and forces. Now it's time to learn about work as it's defined by scientists and how simple machines make work seem easier.
Read the introductory paragraphs to learn the definition of a simple machine and some of the different types. Do the prediction at the bottom of slide 1. Turn to slide 2 and read the background information to learn the definition of work and the units you are required to work in to get your answers to come out in joules, which is the required unit for work.
Now I'll help you work through the 2 sample problems on slide 2. As always, the first thing you do is read through the problem and determine what you're being asked to find.
In problem 1, you are solving for work, so that equation goes in the formula step. And you are given the object's weight, which is equal to the force you need to apply in order to move it, and a distance of 3 meters. Those values are substituted into the formula and the answer is calculated. Because 1 Newton meter is equal to 1 joule, the answer can be rewritten as 58.8 joules.
Now let's look at the second sample problem.
You are given force and distance. These are substituted into the work formula and the answer is 2125 joules.
Now examine the table on slide 3. The intent is not to have you memorize all these terms, but to see that they are all related to the equation work equals force times distance.
The variables highlighted in blue are measured when using a machine, and the variables highlighted in green are measured when lifting or moving a mass without a machine. Flip back to this chart as needed when doing calculations in the rest of the lab. Now read the very important box on slide 4. It tells you the 3 ways that simple machines make work seem easier. Turn now to the data table on slide 8. Notice that you need to measure the force and sometimes the distance used with each of the 3 simple machines being tested.
Now we'll measure the force required to lift this 500-gram mass, which is equal to 0.5 kilograms, a distance of 0.3 meters above the surface of the table. The force required to do this is Fr because we're not using a machine. So here's 0.3 meters. This is the force sensor and the LabQuest. I'll lift slowly and steadily. And you can see the reading varies between 4.967 up to 5.0.
You fill in Fr equals 5.0 newtons as measured on the LabQuest and Dr equals 0.3 meters because that is how far the 500-gram mass was lifted in the direction of the applied lifting force. You now have the numbers needed to calculate the work output, WO, which is the work done to lift the mass 0.3 meters above the surface of the table without a machine.
This time, my task is to raise the same mass 0.3 meters above the surface of the table, but to do it using the simple machine called an inclined plane. In order to do that and to get it to this height using the inclined plane, I have to slide it this entire distance. That distance is 0.9 meters. So I drag it slowly up the inclined plane at a steady pace.
The average force reading is approximately 2.5 newtons. This force and this distance are used to calculate the work input for the inclined plane. Fr from the first column is inserted into the mechanical advantage equation together with the FE of 2.5 newtons for the inclined plane. From the first column, WO is inserted into the efficiency equation with WI just calculated for the inclined plane. The dividend is multiplied by 100 and the efficiency is expressed as a %.
Now this time I'll perform the same maneuver using the simple machine called a lever. Again, I raise this mass 0.3 meters above the surface of the table, and when this is parallel to the table, this is indeed 0.3 meters. I'll attach the force sensor and pull down steadily and slowly. And at that point, it's 0.3 meters above.
The lever allowed me to apply a downward force to raise the mass upward. I applied an FE of approximately 5.0 newtons and a DE was again 0.3 meters. Put these data points into the table, then calculate work input, mechanical advantage, and efficiency, just as you did for the inclined plane. Note, FR and WO are the values from the first column.
This time, I'm going to raise the mass, again, 0.3 meters above the surface of the table, which is this distance, by pulling downward on the string wrapped around the pulley. You can read the force I need to use off the LabQuest.
Again, the pulley allows me to pull with a downward force to raise the mass upward with an approximate force of 5.0 newtons over a distance of 0.3 meters. Put these data points into the table, then calculate WI, MA, and efficiency, just as you did for the inclined plane and the lever. Note, FR and WO are again the values from the first column.
Now go ahead and answer the questions on slides 9 through 11.